Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syahmi bin Johari. So today our group we will present about tensile test experiment. So this is our group members and this is content of our slide. So I will present about the introduction. So the introduction about tensile testing is the most fundamental mechanical test that can be performed on a material. Tensile tests are simple, inexpensive and fully uniform. We may quickly assess how a material will respond to tension forces by pulling on it. We find the material strength as well as how much it will stretch when we pull it. Next, tensile testing may disclose a lot about material properties. We will have a lovely, complete tensile profile if we continue to pull on the material until it breaks. It will produce a curve indicating how it reacted to the applied forces. So lastly, the point of failure on the graph is commonly referred to as the ultimate strength or UTS. So this is the example of graph where is the stress versus strain. So we can see there the ultimate strength and the slope, the graph is the Young modulus. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafizuddin bin Badrillah, and for this day I would like to present to you about result of this experiment. So this is table 6.1 parameter of specimen before testing, and as you can see, the average of diameter for aluminum is 8.14 millimeter, and the average diameter for my steel is 8.04 millimeter, and for gauge length, the average for aluminum is 85.14 millimeter, and average of gauge length for my steel is 88.1 millimeter. So the next one is result for table 6.2 parameter of specimen after testing. So the average diameter for aluminum is 6.38 millimeter, and the average of diameter for my steel is 6.8 millimeter. And the last one is gauge length for aluminum is 92.86 millimeter, and gauge length after testing for my steel is 101.86 millimeter. That's all from me. Thank you.
Next is observation. To achieve reliable and repeatable findings, we must use a correctly sized force, gauge, or load cell sensor depending on the projected load measurement. Using a sensor that is between 20% and 80% of the predicted load measurement is a good rule of thumb. This will help prevent overloaded circumstances at the top end of the measurement range and avoid or reduce incorrect findings at the low and related to mechanical noise. Another typical source of faulty tensile readings is using the wrong test fixture. A fixture that is too big for the sample or provides too much gripping force to the sample during tensile movement might cause the sample to fracture outside of the required gauge length range. The test fixture should be sized according to the predicted load characteristics of the sample because they deliver force to the sample as actual loading rises, which action test fixtures function well on ductile samples but are less dependable on brittle materials. The specimen should be gripped such that the two ends of the specimen are covered by the grip. It is important that the specimens are tightly gripped onto the specimen grips to prevent slipping, which will otherwise result in experimental error. Next, we must ensure the specimen is vertically aligned, if not a torsional force rather than axial force will result. We cannot come close to the equipment when the tensile test is running and always wear safety. BCC structure in mild steel whereas centered FCC structure in aluminium. When the material is loaded, changes in length show its ductility. In my steel, there was a lot more necking than in aluminium. The elongation of the specimen is affected by precipitation, hardening of aluminium and related laws. When subjected to the same amount of load, there was relatively higher extension in aluminium than in my steel. This can be attributed to the difference in microcrystalline structures of the two sample. Lastly, my steel reached a yield point at a stress on a higher point than aluminium. Therefore, it can be seen that my steel obtains higher tensile strength in comparison to aluminium.
Okay, Assalamualaikum. My name is Muhammad Ridwan Bero Haizat, matric number CD210031, and I will talk about my part, and that is the calculation. Okay, first of all, we need to get the percentage reduction of area and percentage of elongation. For percentage reduction of area, we use area before minus area after divided by area before times 100%, and percentage of elongation, we use length before minus length after divided by length before times 100%. Okay, and the result This is the result for reduction of area. For aluminium, we get 38.57%, and my steel is 28.56%. For percentage of elongation, for aluminium, we get 9.07%, and my steel is 15.62%. Okay. For young modelers, we use gradient of stress minus strain, and we get it by graph. The left graph is for aluminium, and the right graph is my steel. Okay, this is the result for young modelers. For aluminium, we get 11.428 gigapascal, and my steel is 93.75 gigapascal. Okay, that's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I want to present discussion experiment for tensile. First, mixed steel had a greater young modular than aluminium. Need a great deal of energy to bend and strain mixed steel, whereas aluminium required less force to bend and strain. Mixed steel had a higher yield point than aluminium, which result in increased strain resistance and particular strain at the certain temperature. As the result, we must remove or add the specified value from each measurement. The mistake in the Gauss reading will reflect the strain calculation, the elongation, and also the pattern of the graph. Last, we must exercise extreme caution when handling specimen and conducting the experiment in order to eliminate any potential of error.
Next, for the conclusion. As a conclusion, the experiment that we did was a success. We managed to conclude that mild steel and aluminium have two different mechanical properties. For mild steel, it shows that it has higher young modulus. It also shows that it has higher yield strength compared to aluminium. Other than that, mild steel shows ultimate tensile strength. This experiment also shows that elastic and plasticity deformation occur when the necking process and the diameter of material will become thinner as the process goes until the end. To improve the results of this experiment, we can try to repeat the experiment to get more results so that we can find the average for all the data and get more accurate results. Other than that, to reduce error handling the experiment, we can use vernier caliper to measure the specimen more accurately.